What is the most extreme thing the universe has ever created? Not the hottest star, not the brightest explosion, not even the densest object we can imagine. Somewhere in the vast darkness of space exists an object so massive, so dominant, that it bends time itself. An object whose edge is so enormous that light would take days to cross it. This is not science fiction. This is real. And today, we are climbing the ladder of cosmic extremes, from stars that burn for millions of years, to remnants so dense they crush atoms, to gravity so powerful that reality itself breaks. At the very top of this ladder stands TON 618, the most massive black hole ever discovered. But to understand why it is the ultimate extreme, we must begin much smaller. The universe does not jump straight to its most terrifying creations. It builds them step by step. Each extreme is born from the failure of the previous one. Stars exist because gravity tries to collapse matter, and nuclear fusion pushes back. When gravity wins a little, stars grow larger. When gravity wins completely, stars die. And when stars die, they leave behind the most extreme objects known to physics. This is the ladder of extremes, and the first rung is something very familiar. Every star begins the same way. A cold, drifting cloud of gas, mostly hydrogen, collapses under gravity. As the cloud shrinks, it heats up. When the core reaches millions of degrees, hydrogen atoms slam together hard enough to fuse. This moment changes everything. Fusion releases energy, and that energy pushes outward. Gravity pulls inward. For millions, sometimes billions of years, these two forces remain perfectly balanced. That balance is what makes a star. Our sun does this quietly and steadily. But massive stars? They live fast. They burn furiously, and they're destined for violent endings. Some stars are born with tens or hundreds of times the mass of the sun. These stars swell into red supergiants and hypergiants, so large that if placed in our solar system, they would swallow the orbits of planets. But size is a weakness. The more massive a star becomes, the faster it burns its fuel. Fusion races out of control, and eventually, the fuel runs out. When fusion stops, gravity has nothing to fight against, and gravity never loses. The death of a massive star is one of the most violent events in the universe. In less than a second, the core collapses. Electrons and protons are crushed together. Then, boom, a supernova explodes with the energy of billions of suns, briefly outshining entire galaxies. These explosions create heavy elements: iron, gold, uranium, the very atoms in your body. But what remains at the center is something far stranger. When the core collapse stops just short of total destruction, the result is a neutron star. Imagine the mass of the sun, crammed into a sphere only about 20 kilometers wide. A single teaspoon of neutron star material would weigh billions of tons. Atoms no longer exist. Electrons are crushed into protons. Matter becomes a sea of neutrons. This is as dense as matter can get, without breaking the laws of physics. But some neutron stars don't just sit quietly. They spin. When a neutron star spins rapidly and emits beams of radiation, it becomes a pulsar. Some pulsars rotate hundreds of times per second. As their beams sweep across space, we detect them as precise pulses, so regular that some rival atomic clocks. Pulsars helped us confirm Einstein's predictions about spacetime. But even pulsars are not the most extreme neutron stars. There's something even more violent. Magnetars are neutron stars with magnetic fields so powerful they defy intuition. Their magnetic strength is trillions of times stronger than Earth's. If a magnetar passed halfway between Earth and the Moon, it could erase every credit card on the planet and tear atoms apart at the molecular level. Magnetars crack their own crusts, causing starquakes that release deadly gamma-ray bursts. Yet even magnetars are still resisting gravity, and eventually, gravity demands total victory. If a collapsing core is too massive for even neutron pressure to stop it, collapse becomes unstoppable. The star implodes into a black hole. No explosion, no surface, just a region where gravity becomes infinite. At its boundary lies the event horizon, the point of no return. Cross it, and not even light can escape. Time slows, space curves, reality breaks, but black holes come in sizes, and the largest ones rewrite the rules of the universe. At the center of almost every galaxy lies a supermassive black hole, millions or billions of times the mass of the sun. They feed on gas and stars. They power quasars, the brightest objects in the cosmos. And among all of them, one stands above the rest, not by a little, but by an unimaginable margin. Ton 618 is not just large. It is 66 billion times more massive than the sun. Its event horizon is so vast that light would take days to cross it. If placed at the center of our solar system, its gravity would dominate everything far beyond Pluto. Ton 618 isn't just the biggest black hole we know. It is a challenge to physics itself. How did it grow so massive, so early in the universe, without tearing its galaxy apart? These questions remain unanswered.